Good morning. So thank you so much, Dr. Adhikari and Ashna, for accepting my invitation for this presentation. We have 14 outstanding students and also our outstanding graduate teaching assistant assisting in this program. So thank you for that. And I already mentioned about the presenter and the mentor. So Asna is high school junior or senior, Asna?
I'm going to sophomore year.
Oh, you're sophomore. Okay.
Yeah.
Okay. Thank you. So high school sophomore in a school in North Carolina, and Dr. Adhikari is a professor at Fayetteville State University doing fantastic research. So with that, I would like to request you for sharing the presentation. Thank you.
Good afternoon. My name is Ashna Upreti, and I am a student at Jackport High School in Fayetteville, North Carolina. This presentation is about crystallography and electronic structure of tantalum-4 carbon-3. I worked on this project with Sanaya Lyles, Elizabeth McBrayer, Boj Gautam, and my advisor, Chandra Adhikari. Thank you to the U.S. Department of Energy for supporting this project. I would like to acknowledge Fayetteville State University for the research facility and Dr. Chandra Adhikari for mentoring and advising. So what are Mxenes? The family of Mxenes consists of carbides, nitrides, or carbon nitrides of transition metals. They are two-dimensional nanolayers with the thickness of several atoms and a planar size in the order of several micrometers. Mxene materials have a wide range of unique properties that make them attractive and suitable for a variety of applications. For example, they have a large specific surface area and high mechanical, electronic, and physicochemical properties, as well as excellent biocompatibility. The diagram on the right shows an image of the structure of a Mxene, and we got our information from the source listed at the bottom. Mxenes are an early transition metal carbide, nitride, or carbon nitride. They were first discovered at Drexel University in 2011. The chemical structure of Mxene is M(n+1)xN. The M represents a transition metal, in this case tantalum. The X is carbon, nitrogen, or carbon nitride, and the number ranges from 1 to 4, and in our case, this is the number 3. How are Mxenes applied in the real world? So Mxenes can be in the fields of energy, catalysis, optics, electronics, synthesis and processing, mechanical, electromagnetic, environmental, and biomedical fields. Their high electrical conductivity is suitable for electrodes for energy storage devices like supercapacitors and batteries. Their large surface area and ability to be functionalized is suitable for drug delivery systems, and this facilitates intercalation of ions, which is beneficial for energy storage applications. These are also used in lithium-ion batteries, sodium-ion batteries, and supercapacitors. Their high photothermal conversion efficiency is used in photothermal therapy and photodynamic therapy for cancer treatment. And our reference is listed below this diagram. How are Mxenes synthesized? So Mxenes start as tantalum-4, aluminum, and carbon-3, and they are etched with hydrofluoric acid, which removes the aluminum. Then they are intercalated with tetrapropyl ammonium hydroxide, resulting in tantalum-4 carbon-3 nanosheets. Then they are modified with polyvinyl pyrrolidone. Our source is listed at the bottom. The Mxene crystalline structure And this is the computationally optimized structure of tantalum-4 carbon-3, shown in the diagram on the left. The space group is R3m number 160. The lattice parameters are A and B are equivalent to 3.13095 angstrom, and C is equal to 30.76163 angstrom. The volume is 261.1513 angstrom cubed. The alpha and beta angles are equivalent to 90 degrees, and the gamma angle is 120 degrees. Power diffraction pattern. Power diffraction pattern is a technique using X-ray diffraction on powder samples for characterization of materials. This works by irradiating a material with incident X-rays and then measuring the intensities and scattering angles of the X-rays that leave the material. These are commonly used to identify unknown materials, quantify the amounts of different phases present in a sample. In tantalum-4 carbon-3, the first peak appears at 2 theta, which is equal to 33.5 degrees for the 1, 0, negative 2 plane, shown in the diagram on the right. In tantalum-4 carbon-3, the most intense peak appears at 2 theta is equal to 36.2 degrees for the 0, 1, 5 plane in the diagram on the right. Formation energy. Formation energy is the energy change when a compound is formed from its constituent elements in their standard states. The formation energy is calculated by subtracting 4 times the energy for tantalum and 3 times the energy for carbon, and subtracting it from the formula for tantalum-4 carbon-3. Then it's divided by 7 to find the energy per atom. In the diagram on the right, we can see Ti4C3, Ta4C3, and other compounds and their formation energies. And one thing in common with all of these compounds is that they all have a negative formation energy, meaning that they are all chemically stable. We can compare this to the diagram on the left, which is from our previously published paper, which has the compounds Ti2C, TiTaC, and Ta2C. And these also have all negative formation energies. We can see that, however, Ta4C3 has a more negative formation energy than the diagram on the left, and that tells us that it is more chemically stable. Band structure. Band structure maps out the energy levels available to electrons as they move through the material. In the figure, energy values are shifted by the Fermi level. Ta4C3 is a metallic conductor, and Ta4C3 has no band gap, as you can see in this diagram. Density of states. The higher density of states, the more easily electrons can flow. The 5d states of tantalum and 2p states of carbon dominate the density of states in the valence band. There is a non-zero density of states at the Fermi level. At the Fermi level and in the conduction band, density of states is dominated by 5d states of tantalum, as you can see in this diagram on the right. In summary, we used VESTA for crystallographic visualization. We used VAS for density functional theory calculations. Ta4C3 is metallic. In the valence band, the density of states is dominated by 5d states of tantalum and 2p states of carbon. The density of states near the Fermi level is dominated by 5d states of tantalum. Thank you so much for viewing this presentation.
Okay, so thank you so much, Ashna, for this presentation. Probably we'll unshare the screen, and then there are a few questions. As I sent you, like, how did you approach your current mentor to secure a research opportunity? Like, could you please kindly answer that? Would be very useful to our students.
Yes, so when I first wanted to approach my mentor, I looked up online like universities near me. And near me, there's this university called Fayetteville State University, and that's where my mentor teaches. And I looked in like the faculty directory, and from there you can actually see like emails of professors and their specific departments and areas of teaching. So like whatever field you're interested in, you can always reach out to them because they provide all the emails there. And that's how I really reached out to my advisor. And yeah, so
Great.
you might not always get a reply on the first time, so it's always good to like reach out to multiple people at once.
Nice. The next question here is, how do you manage your time for research, as you must be busy in your coursework, like a lot of homework from your different courses, like so you are doing research now. So how do you manage balance your coursework and time and then research?
Yeah, so I take a lot of AP classes. You guys probably take them too. They're like college level classes you can take in high school. So yeah, there's a lot of coursework I have to manage with. And I like making personal schedules for myself, just using like the Google Calendar online. And I think it really helps me stay on schedule throughout the day, like setting aside an hour to do homework and then maybe like you take a break and then after that you work on your research for an hour. So I think that's always helped me a lot.
Thank you so much. And I send you the third question. Do you enjoy doing physics research?
Yes, I do enjoy doing physics research. In the future, I definitely do want to be involved in a scientific field, maybe medicine, but I think it's been great exploring physics.
Thank you. And the last question is, for my students, our students here, if you have any suggestions to other high school students or here students here who are interested to find a research mentor, like what do you have any suggestions?
Yeah, I think if you want to start doing research, I think you should just go for it. Like, start looking up universities near you and look up fields of like professors that are in the specific fields that you're interested in. And like, don't be scared to reach out to them. There's so many people that are so willing to help high school students like us. And even if you don't get a reply on the first time or they'll like decline you, like, don't be dismotivated. Like, there's so many people out there who are so willing to help high school students.
Thank you so much. Like those were kind of pre-prepared questions. I thought those kind of questions will be helpful to you, and so I sent those questions to Asna, and Asna tried her best to answer those questions. Hopefully, you got the answers. I was happy with those answers. But do you have any other questions which I did not cover, for example? Sophia?
We cannot hear that. Could you please recite that for us?
Yeah, I'll repeat the question. Yeah.
How did you like decide the topic?
Oh, that's an excellent question.
Okay, how did you decide the topic, Asna?
Yeah. How did you decide the topic? That's right. That's the question. Professor Adhikari, so or Asna, actually, the question is.
Maybe let me Asna to respond that.
Yeah, Asna. How did you choose the topic?
Okay, so originally I was just like interested in the field of physics whenever I reached out to my advisor, but I wasn't really sure what I really wanted to research in that specific field. So he like listed out a few options that he had in mind because he's obviously a physics professor, so he knows a lot about the field. So he gave me options and then Mxenes is one of the options. So that's how I came to study that.
Good. Thank you. Any other questions? Do you have any other questions? Any questions to Professor Adhikari? Like any kind of question? So, Professor Adhikari, would you mind telling my students about Mxenes? Like, how did you actually come up with Mxenes research?
Yeah, that's a nice question. So we realized that the Mxenes was discovered in 2011. There are a lot of possibilities of Mxenes. There are lots of possibilities like the technical approach. There are many things people talked about, but there is only one Mxene which people talk a lot, like the Ti3C2, tantalum 3 carbon 2. then that's a great avenue to search. And if we can use them for in the technological advancement, then that's the one area we have to look into that. This is what we thought, and we wrote a proposal. We got that proposal accepted, and then we get started working on it. So this is more about the filling the gap. So we saw a gap in Mxenes of the 2D materials mostly, and then we are trying to fill the gap.
Thank you so much. Any other questions? Okay, so like again, these are very enthusiastic students, and they are like junior and senior, want to go to research in physics. Do you have any tips, Professor Adhikari, from when you observe high school students? I know you mentor many high school students, undergraduate students. Like, so do you have any tips, like couple of tips to my students, our students here?
Yes, like Ashna said, so we do have workload and the teaching load in the university, but we wanna prepare the high school student. Like if we can give some research experience to the high school student, my experience is that they're gonna thrive pretty well, and then they're gonna do pretty well in the university as well. So one thing is that whatever research experience you get, that's gonna add up. So it doesn't have like when first time Asna came to me, she said like she may possibly go to the medical. So, but it doesn't mean that she cannot do the research in physics, right? So because when you are doing the PhD, like for example, if you are doing the PhD, if you want to be in the medical field, do PhD in the medical field. If you want to get your expertise in physics, let's say you want to do the PhD in biophysics, then do PhD in biophysics. Don't go to the chemistry professor when you go to the university. But when you are in the high school or when you are in the undergrad, it doesn't matter where you started. Like for example, even to know how the research works is the great learning. So if you like, for example, how does research work? Like for example, at the first you're going to decide the project, and then this project may or may not work. This is what you're going to learn later on. This project may or may not be successful. Then first you decide the project, and then so you're going to work on it. Your experiment may fail. Sometimes your hypothesis may fail. The learning that hypothesis may fail is also the great learning, great understanding of science. And sometimes your hypothesis is going to be successful. And then you're going to set up your experiment, or you're going to set up your design, research design. You're going to do it. And then if you find the research promising, and then if you find your finding promising, then you're going to come up with the write-up. And then you're going to prepare a manuscript. You're going to send that manuscript to the editor, and editor may decline. That's also the point to learn. And then editor may decline or may send that to the reviewer, and then reviewer is going to send up with many questions. Then some of the question you have to redo to answer that, you have to redo the experiment again. And then you have to redo the research again. And then you redo it, and you're going to convince many people, and then it finally going to be baited to be published. So to learn the process, how research works, and it is also the great learning. So it is also the great thing to learn when you are in the high school or the undergraduate level. So that's why if you just contact with a person, should be relevant. Like for example, if you're into the science, possibly you don't want to go to the social science, or like for example, if you are dedicated to do, like for example, let's say I want to do physics, then possibly you want to go more towards physics or physical science, like physics or chemistry. But any professor, if you reach out to any professor, then you contact them. One thing, and second thing is that not all professors may be willing to take you in the research project because you are a high school student. Let's think in the different perspective. Like if I take the high school student because I want to help them, and then I want to prepare them, then I want to take more high school students. But for other professor, let's say they have a grant, they have to complete the target. They have to complete the target. They have to show the result, what they got. Then with the high school student, obviously, I'm not blaming, but obviously productivity is going to be a lot less than the graduate student. I mean, you don't mind that to learn, to know this, because like whatever I do, that's the advanced beyond the advanced calculus. So whatever Asna is doing is beyond the advanced calculus. then what I actually do, I break the project into a smaller part. I give the project whatever Ashna can do, a little beyond that she can do. I'm going to give that project, but which is far beyond that she cannot do at all. I'm not going to give that project to her, that part of the project to her. That means your advisor going to know, your advisor knows what the project is. We have to give that to the high school student, and what part of the project the advisor themselves got to do it, or they have to give that to the graduate student or maybe the undergraduate student. So if you reach out to the professor, some of them may decline. Like this is what Ashna said. Possibly she learned that from her friend, from her peer. So some professor may decline, and sometimes, like for example, I have 7 high school student and then 5 undergraduate student. Now, if someone asks me, then possibly I got to ask them to wait for a semester or 2, right? Because I cannot take more than I can. More than I can advise or mentor at a time. So some professor may decline or may say that maybe they possibly do not demotivate you, but they say that, okay, I cannot take it. Then they reach out to the other professor. Means that doing similar project is always you don't have to be kind of like the rigid to the particular project. You can go little left or right, so that you still gonna get the experience. So any kind of experience gonna help you, because it is more about learning how does research work than giving the productive research when you are in the high school student, at least in the high school, or maybe the early undergraduate level as well. So reach out.
Thank you.
Reach out.
Thank you. Thank you so much, Dr. Adhikari, and thank you so much, Ashna. Let's give big hand to the speakers. Thank you.
Thank you all. Thank you for giving us the time.
So,
Thank you.
yeah. So have a good rest of the day. Thank you.
You as well. Thank you all.
Thank you. Bye.
Bye.